So, hello again everybody, and today we are going to try create encoding and decoding matrices for our Hamming code depending on whichever you have. So there are three options here. One is Hamming systematic code, another is Hamming non-systematic code, which is different in the order of symbols, and that's it. So our matrices will also be different in the order of rows, columns, etc. And finally, there is also a cyclic codes. Now I have updated the materials for you. Please double check that everybody is not missing here. I believe I updated the latest version here. So now everybody who has a cyclic code has a corresponding generating polynomial specified for you, which matches all the requirements, meaning that it should produce sufficient amount of reminders, but I still would recommend you to double check it. And if you see any mistakes, yes, don't hesitate to contact me. It might just as well be that I, missed some number here, and because of that, that polynomial is no longer valid for you. Yes. So you have basically main parameter is the length of your code word. Yes. So we discussed as example of the length of 7. But as you can see for your tasks, this length can be slightly greater. Again, this might be and somewhat as an issue, for example, like having group calls of length of 31 when you will need to create that schematic. But it's not like making it difficult, it's just going to be a big schematic. Yes, but then again, more or less, I believe nobody has length of 7, minimum is 15, so it's not that big difference anyway. Okay, so we'll focus entirely on these two columns today, yes, the error correction code and error correction code parameters. All the others, more or less, we have covered, except the task 6 or 7, I believe. Let's now double check. So what we'll be covering today is the task number 5, error correction code with specified parameter by coding and decoding operations for your data block. So if you can, of course, it is still better that you actually show this, for example, for cyclic code as this division process. So then I will understand that you really understand everything. And of course, uh, that will be more clear for me. But still, if you find it too difficult for you, don't hesitate to use this code that we have created today, because at least that's going to, if you did it properly, yes, not make a mistake somewhere in the step, I don't know, somewhere here, which is going then to ruin your entire answer. Yes, because here you have to be careful, especially if you have long code word. Then, well, yes, you need to be concentrated while you do this division. So for that reason, why I provide you this code, which we will make together today, so that you can check yourself if you did it properly or not. But again, of course, you can verify that even without code, because you know that if you did incorrectly code word, then dividing it with a generator polynomial, for example, should produce 0 reminder. So if you did something wrong there, you will not get a 0 reminder, and you know that somewhere there is an error. Yes, but either way, it's still better to have kind of correct answer for your task, yes, to compare with. Yes, so what we will do here will be encoding and composing, I believe writing, yes, code word depending on systematic or non-systematic for you. Check it for errors without introducing any. Check it for errors after we introduce one single error, and check it for errors after introducing a double error. And since we will be using a matrix approach, I'm going to show you how we can do these B, C, and D three tasks with just one line of a code. Yeah, well, a little bit exaggerated, but the procedure of decoding is actually going to be just one line of a code, which is very convenient. And obviously then you will need to design and put into report schematic diagrams, which I have explained already for group code and for cyclic codes. Then, at the conclusion of this course, I believe in the very last week of May, yes, we will return here with your encoding and decoding matrices and add them inside of the simulation program that's going to tell you how exactly your code works in somewhat like, well, closer to real world situations where you have some noise, specific modulation type, yes, symbol duration, energy, all that stuff, and then how well it works in the certain signal to noise ratio. But that is going to be our final and the most difficult task, for which we will today design matrices. So matrices we will design today can and will be used in this task B, yes, later. So we do some future work as well. So okay, let's go then to the MATLAB or Octa, whichever you prefer, and let's begin with the group code. So we'll go through all the cases. You may make a copy of each of them, yes. Uh, so that might be useful for you in exam tasks, not exam tasks, but final tasks, which I will distribute among you. This is kind of exam. Or you may focus specifically on your specific course project task, whichever is necessary. The coding and decoding procedures are going to be exactly the same. What will be different is how we create a matrix. Again, you can do everything completely manually. So let's say now here I have stricken out this control symbol reminders, left with these ones, read them here, add identity matrix in front of it, and that is my matrix, which you can actually go straight away and input if you already have it. No reason not to do. Then you can, well, uh, CLC, clear variables. So you can input it straight away like that. 0, 1, 0, 0, 1, 1, 0, and wait, no, it's here. So that is it. Yes, basically, if you have it. But if you don't, you need to design it first. So for group code, it's very easy actually. Yes, because these syndromes for group code come in the correct order, like 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. And as you can see, for cyclic code, it's not exactly the same. So you will spend a lot of time to actually get them first to create this matrix. For this, it's very recommended, I would say, yes, to use computer to aid you with that, especially if you have length of 31. Some of you have length of 15, which is maybe possible to be done manually, but some of you have length 31, which is boring, honestly, doing the same operation just like a computer over and over again. Yes. So I will show you now how we can create this entire matrix. So we'll start with the group code for which the syndromes are specified in the natural order. Yes. So first thing first, we need to get the table of syndromes and table of error vectors, yes, to match each other and maybe output them. So I'm just going to comment this one, not really wanting to erase it, that I have inputted. So that is going to be group code non-systematic. Probably the easiest case. Well, they are all more or less the same, but this one will be the easiest one because everything is just in the natural order. So what you need to specify is obviously your parameter m, which in my case is 7. Yes. So that's numbers will need to go through from 1 to 7 in binary form. And specifically, let's call this as a syndrome, which is going to be just like that, numbers from 1 to m. I'm going to make them as a column. So if I output them, now I have these syndromes, but they are in decimal form. What I want to have them now would be in binary form, and we are set and ready, basically, yes? So let's do that and convert them into decimal or binary form. So specify syndromes in decimal form. Now we convert them to binary form. For binary conversion, we are going to use a built-in function called dec to bin. Yes, so that's as simple as that. Dec to bin for syndromes. Let's see what's being output then. Then you can see them as a text. Yes, you see type of it is character, which is still almost what we wanted, but we will want that to be numbers because we are going to do some operations with that. Matrix product, adding with XOR, and so forth. And we can't do that with characters because that's going to not work properly. Yes, so let's say I'm going to add +1 to everything, and then you see now it's suddenly 49. Yes, which is the ASCII symbol code for 0 and 1. So that's not working like we wanted to. So because of that, what I'm going to do now is to check whether each of these text symbols is character symbol 1 in quotes. Yes, so that corresponds to the handwritten, not handwritten, but the type digit 1 as a text. So we compare it, and if it is 1, then it's going to return a logical number 1, not the character anymore. And if it's not, then it's going to return a logical 0. So if we do that, now you see that our answer is of type logical. And we can do stuff with that as we want now. So for example, adding +1 is naturally going to convert zeros to 1, to ones to 2. Yes, and so forth. So now we have this, which in fact is the syndrome table. Yes, so syndrome matrix. Now we have done this second part very easily, yes, which was getting this decoding matrix, yes. So we actually already have that, and that's going to be for systematic or non-systematic, sorry, group code. What I want to do now with that is to actually strike through from there every power of 2 position. That would be 1, 2, 4, 8 if you have it, 16 if you have it, and so forth. So I only want to keep those which are not power of 2. Now that is a little bit tricky, but not impossible. What we want to do is to implement something called logical indexing. Yes, logical indexing does some access to the cells, rows or columns, depending on certain condition, rather than specific numbering, like first, second, or third. So for example, I can say, let's maybe rerun it again, just to save this as a syndrome matrix. Syndrome matrix is like this. Say now I want to display only those rows which are odd numbered, like 1, 3, 5, or 7. Yes, so for that, what I need to do is to say, well, first of all, I need to have some indexes, which will be, well, which will be actually syndrome, I believe. Yes, we have them. So syn needs to be uh, calculated as a modulus of syn versus 2. So now you see the reminder of dividing the syndrome value 1, 2, 3, 4, 5, 6, 7 by 2 and finding the remainder. Yes, and we only want to keep those which are 1. Yes, so I'm going to specify these. Well, it seems like logical, yes, but the answer is actually double. So let's see if it works right away. So what I'm going to do now is to say that I'm going to use this entire expression as the number of the row that I want to keep, and I'm going to keep all the columns. Now that's not going to work because it has to be either integer number or logical, but it cannot be double. Yes? So because of that, I actually need to convert it somehow into logical. Well, that's actually very simple, and I'm going to say, is it equal to 1? If yes, that's going to be logical 1. If no, that's going to be logical 0. So then number-wise, they are exactly the same. Yes, so I'm now going to do the same operation, like so. See, these numbers seem to be the same, but in this case, they were double format. In this case, they are logical format. And if you use logical as indexes here now, where is what was that? Okay, it's easier just to copy that again. Uh, is it equal to 1? So I use double equation to check if it is equal, not to state that it is equal. Yes. So then it's going to work, and it only kept the first, the third, the fifth, and the seventh row. Now what we want is some other condition, is whether it is power of 2. So how should we then formulate this condition that this is a power of 2? Well, there are multiple ways, but mainly the easiest one would be calculating the logarithm of base 2. So log 2 over the syndromes would be like so. Here it is 0, zero point 0, here it is 1, here it is 1.5, here it is 2.0, 2.3, 2.5, 2.8, 3.0, and so forth. So if this logarithm is a, well, we can say integer number, then that is the power of 2, and that means we are there. However, um, how do we check if it's an integer if all of them are double format, floating numbers? So we need some trick here to do it, yes? Well, we could just check it. um, is integer, I believe, if there is such command. Is invalid correct, isn't it? Yes, there is such. Let's say 10. Well, 10 is integer, or is int. Okay, now uh, we could probably try to convert it, but that would convert them and route them all. Yes, which, no, not remembering specific command, but okay, that doesn't matter. So what we need now to figure out is how we should treat these, whether it's having a fractional part of 0 or not for the fraction. Yes, so I believe there was something like fractional. Let's double check then. Almighty Google, MATLAB fractional part. So what we want to do is to separate the fractional part and see if that fractional part is 0. Yes. Um, yes, that was probably fixed. Yes, I believe I have seen that. Yes. So kind of what we want to do is to first separate the integer part, decimal part, and then what's left is the fractional part. So not sure there is a specific command to do this, but let's try now fix 2.8. Now it is 2, and if we do 2.8 minus fix 2.8, then it's 0.8. Yes, so what I want now to do is to have this log 2 saved as a number, a minus fix a is going to separate the fractional part. And what I want now to check if it is equal to 0. Now, none of them is roughly equal to 0. But, well, actually, it passes. Yes, it's not exactly 0 because there is something 0, 0, 0, 0, 1, but it's considered small enough to actually match. So, with that in mind, actually now we have found a way to separate the control symbol positions and um, information symbol positions. And that will be useful for us when we will try to make a systematic code as well. But for now, we wanted that just to strike out the control symbol positions. So we'll denote these positions as index E, considering that E is what we use for control symbols and C is what we use for so find logical positions for every control symbol, which would be E1, E2, E3, and so on. So this index, logical index, is therefore the comparison of fractional part of logarithm with 0. So what we want to do now is to calculate log 2 of syndrome. Then we want to subtract from this logarithm the integer part. So basically what we do is we just throw away, or you can say round down floor, yes, the fractional part, yes. Now, however, you need to be careful with that because floor for negative numbers would actually round them up and change this base, yes. Now, fix does not do that. It actually just throws away anything that's after decimal point, regardless of the sign, yes. So that's more accurate, actually. And what we want to do now is to check if it is 0. So let's run it once again just to see if it still works like expected. It works, yes, and accordingly, well, checking if it's equal to 0 is a little bit risky, yes, because it might be not so stable. However, much more accurate would be if it's less than, let's say, 0.0001. Yes, it would be more accurate and more robust. So let's maybe keep it like that, because all the other ones are significantly more than this. And although they display as 0, log 2 of syndrome, yes, 0, 0, 0, somewhere there might happen non-zero element which will ruin it, and it will say no, it's not exactly 0, it's very, very small, but still not 0. So because of that, no, it's not. Yes, and if you say okay, if there is anything after the 6th position after the decimal point, we just ignore it, and that works differently. Yes, so that's more reliable way. Okay, now that we have found it, let's now separate uh, syndromes for information symbols by reading specific number of rows. Yes, so that's going to be, well, part of encoding matrix. Yes, which is going to be syndrome matrix oh, sorry, number of row matching index E. Well, actually, not index E. We want to remove those index E and not to keep them. So these are accordingly indexes of control symbols. And now we want to have indexes of information symbols, which are inverse of that. Yes, so index C would be inverse of index E, which is now indexes of information symbol. Indexes information symbols. So here we want to use index C to keep only those which corresponds to the C symbols in our matrix. So here, for example, yes. Now you know that for group code they are located in between in non-systematic way, which we now discuss. So we keep that part. And column-wise, we want to keep them all. Now let's see how our matrix will look like. So let's maybe open up the same material for group code, which I was showing you a week ago. Well, not a week ago, last week. 2 weeks ago, actually. So here we have them separated now. These, yes. Now we don't need to transpose them. We needed to transpose them because we actually created them from scratch by using these equations. Now what I'm doing is actually using this table of syndromes, so it will be formatted as necessary right away. Yes, 110, 101, 011, and 111. But we may need to flip that. Let's check it if it is the same or not. Yes, it looks like we actually have them in the opposite order now. Oh, sorry, it's the wrong one. 110, while we have 011. Yes, so we actually now need to flip it horizontally. Well, that's not a difficult task to do. We just say flip left, right in addition to that command. And now we have it as a necessary. Yes. Well, that happened because our first syndrome column corresponded to the last control symbol. That's why it's a little bit mixed up. But anyway, this is our, how you would put it, uh, equations part of the matrix. Now what we need to do is to create identity I matrix before that and put them in the correct order, depending whether you have systematic code or non-systematic code. Yes? So actually, I'm going to remove it here from that is not non-systematic because up to this point, it's the same for systematic and non-systematic code. What's going to be different is how we now create this matrix. Okay, so let's also make it I, which would be length, or let's say that would be size of matrix encoded matrix, and specifically we are interested to know the number of rows, which is the first dimension. Let's check it. So now what I want to see is identity matrix of 4 by 4. Here it is, yes? Now I want to merge these two matrices to have a non-systematic code matrix. So like here, so this is actually systematic. I want to have non-systematic first. Because for systematic, it's actually much easier. Yes, because for systematic, all that you need to do is say, okay, here is identity matrix, here is the second matrix. You just concatenate them, and that's it. Yes, that's very easy and straightforward. For non-systematic one, it's a little bit more tricky because you have to put your equations matrix in the positions of this power of 2, which we have now as index E. So we have that covered. We know specifically how to access these positions, and all the others in the index C positions accordingly. So let's just do that. Before that, however, uh, let's make some new matrix. Well, let's maybe call this not encoding matrix, but equation matrix. This will be I matrix. And now let's say what we do here is say like that, non-systematic code matrices. So I'm going to create a, well, actually it's the same for both cases, encoding matrix with the dimensions of 7 by 4. Well, actually, let's maybe go here and calculate R as cell log 2 of m plus 1 and K as m minus R. So that is number of control symbols. Control symbols. That is number of information symbols. It's easier like that. Information symbols. And somewhere here I had this size. Now I can simply put K here instead of that, which is size of it. So what I want to do now first is to fill this matrix with zeros. Zeros. Number of rows will be K, number of columns will be M. Yes, so my matrix will be originally like that. So, and what I want to do now is to put this column here, this column here, this column here, and all the others accordingly here, 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 and here. Yes? So that's going to produce non-systematic code matrix. So encoded matrix rows index E, that's control symbols, are going to be our matrix of equations. And encoded matrix positions of information symbols will be accordingly I matrix. And there you have it. Well, no, it actually didn't work out. So index E, it's a column, but I don't think it's actually. So again, it says operator 1 is 3 by 7. What is 3 by 7? I don't know what is 3 by 7. In line 29, it's here, so this line doesn't work. Let's check it. Whose? So 3 by 7. I don't see anything. There is 7 by 3, which is syndrome matrix, but we don't use that. So not sure what it means that it's 3 by 7 and operator 2 is 4 by 3. So, let's check it again. So encoded matrix index E. Let's just to be sure transpose it to be a row. I don't think it's actually matter. No, it's not the case. Okay, let's check then it separately, whatever it's going to display, if it is the same size. Ah, wait, no, it's not going to work in a logical one. So what I would need to do probably then would be like this. So if I do it like this, let's actually try it like this. So I need actual numbers, yes, like 1, 2, 4, 8, and so forth. And I do that by reading them from the table of syndrome, where they come in the direct order. No, it's also not exactly working. But wait, why? Why it's not working? I know. Wait, just give me a minute. I'm going to check a thing. Oh, that's a little bit for future, but it's okay. That's practical. Let's check here. No, it's empty. Not here. Not here. Group code. This one might be it. Uh, no, here I have specified matrix in manually. Uh, and the coding might be actually. So deck to bean, syndrome matrix, flipping, here it is, diagonal matrix, encoded matrix. Wait a minute, I see my problem. I have, of course, I need to put that not in the rows, but in the columns. So the order is like that. Index E, and it's here, index C. So if we run it right like that, now we have the encoding matrix, yes, for non-systematic Hamming group code. Let's also make the decoding matrix as well, while we are at it. Decoding matrix, which will be, well, basically our syndrome matrix, nothing changes there. So it's simple here, yes. So kind of, yes, for systematic code, you will have simpler encoding matrix, but you'll have to deal with decoding matrix then, or rearrange symbols, which again brings you to necessity to calculating these indexes. And for systematic code, it's vice versa, yes. Well, for cyclic code, syndrome matrix is also as decoding matrix, as simple as that, but you will have to get it first, yes. Okay, now just like that, let me demonstrate how to get same stuff for group code, but systematic one. And then we'll do the same procedure for cyclic code as well. Now, To avoid confusion, I'm going to just comment this for now, and I'm going to uncomment once whenever I will need, let's say, systematic code or non-systematic code, and so forth. Okay, so the encoding matrix is, as I said, as simple as to merge together two matrices. We can do that concatenation in square brackets like that. First, we put the identity matrix, that's I matrix. Then we put the equations matrix, and that's it. The decoding matrix, however, will be a little bit more complicated than that. Yes, so here you can see that for non-systematic, decoding matrix is as it was a table, right? Copy paste right away. Now for systematic one, we'll have to rearrange rows, yes, accordingly separating the control symbols and, well, control symbols and information symbols, yes? So rearrange this table, again by using the same logical index IDXC and IDXE. Now this time we do want to access rows, so that's going to be concatenation of syndrome matrix IDX C, first information symbol, concatenated vertically. Yes, so if we matrices merge horizontally, we separate them with comma. If we merge vertically, we separate them with a semicolon, just like numbers. Say, for example, 1, 2, they will be row. 1, 2, they will be columns, yes? And accordingly, instead of 1 and 2, you can use entire matrices easily. So that's going to be syndrome matrix, accordingly index E, like that. So now you see that here, well, for this part, actually, we could have even made it a little bit easier for ourselves, because what we see here is actually the, how we can say, reverse identity matrix when you have ones on the secondary diagonal, not main diagonal. But, well, since we had these indexes already, no point in not using them. So that brings us to matrices for systematic code, yes? Now let's double check if it's what we needed. So it seems, pay attention that we don't flip it, we keep it as it is, yes? So no need to flip it. And accordingly, now let's do the same procedure for cyclic codes. Cyclic code matrices. Now for cyclic codes, you will actually need to perform the division procedure to find all the possible reminders of each error vector and syndrome values. Yes, so let's do that. As I was explaining already, yes, we do get every reminder from the next one. So from this one we get this one, from this one we get to this one, and so forth. And that's actually the logic we use to do error correction by using the second schematic, second division schematic, yes, which was going cyclically through these syndromes until it reaches these syndromes, and that's when it actually does this fixing. So what we want to do now is to actually simulate this, going with this minimum syndrome 0, 0, 1, and going all the way up to the last one. So how should we do that? Well, the best way to organize that would be some kind of for loop when you will do them one by one. So let's say that we want to have some shift register, which will be filled with the 0, 0, 0, 0, 1. Yes? Yes, so zeros and 1 representing accordingly the first, well, the last symbol's error syndrome here. Yes, this one. Now the question is, how many zeros do you need to use? Well, that depends completely up to your R value. In my case, M is 7, so R is 3, and I'm going to actually say that this is zeros R by 1, yes? So that's actually 3 zeros. Let's maybe check it out. 0, 0. Well, let me actually make it as a vector row, as a, not the column. So like that. And I want this last 0 to become 1. So I just say, okay, shift reg end is going to be equal to 1. So now I have the first one to work with. Yes, that's where we started. From this, I want to get next reminder, which would be 0, 1, 0. And I can do that by having shift reg attached by 0. So I append 1, 0 at the end of that and read the last 3 symbols if my first symbol is not 1. So it's not 1. I cannot add generator polynomial here. So I just read these last 3 symbols. Speaking of which, we do need to specify generator polynomial. So gen pol. Yes. In my case, it's, let's double confirm it. Maybe it's different. Z power of 3 plus Z plus 1. So I'm going to add it here as a comment, Z3 plus Z plus 1, which I will write like this. 1 multiplied by Z3 plus 0 multiplied by Z2 in full form, plus 1 multiplied by Z plus 1 multiplied by Z0. Yes? So putting those numbers into the array in this particular order brings me 1, 0, 1, 1. You can separate them with comma or just leave them like that. It's the same result. So that is my generator polynomial, which I am going to need to add after I append this. So, okay. So now I'm going to make the for loop and go through all the possible m cases. So I start with, let's say, j equal to 1 and go all the way until m, which is the maximum number of them. So in my case, it's 7. Yes, so I'm going to have 7 of these, how they call them, syndromes, yes, reminders of division. So what I'm going to do is do it step by step. So first, what I want to do is to say, I just take my shifted register content, append the 0 at the end of that, and save that as some number, let's say A. I don't know, it doesn't matter what exactly. Now from this number A, I want to read as a shift register new value the last 3, well, all values except the first one. Yes? So like that. So we start with 0, 0, 0, 1. See here, we append a 0, then we read these 3 values. Now we get this reminder, which is next. Yes, then we shift it again by adding extra 0 at the end, read the last 3 digits. So that's the next reminder. Then we append a 0 here, and at this point we should not read these last 3 digits, but instead what we should have done would be to add a generator polynomial. So we only do that if we have here 1. And our reminder would then become 0, 1, 1. But it didn't happen because we didn't program it. So it just read the last 3 digits, and until then, it's now fixed, stopping, well, constantly in zeros. So here, that means before that, however, so before reading add generator polynomial if a1 is 1. So that means we need to have if condition a1 is equal to 1, then we do have to do XOR between a and generator polynomial. So as you know, XOR is basically adding together and dividing by 2 and getting it as answer. So that brings us a is going to be remainder of a plus g gen poly, sorry, divided by 2. So here we actually do this adding. If the first symbol is 1, then our if ends. So this if happens only if the first symbol is 1, and then after that, regardless if our if happened or not, we read the last 3 symbols, which are going to be our reminders. So let's see how it looks now. 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, and it starts over again here. Now we actually need to save them also as a syndrome matrix, not just shift reg, yes? So what we wanted to do now is to save it here, syndrome matrix, before we do anything, because we wanted to save this as a first one, 0, 0, 1, as the J row, and accordingly this entire contents will be shift reg. So now our syndrome matrix is going to be like for the cyclic code, like it's here. See? 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 3 ones, 1, 0, 1, which is actually this table. Well, not exactly this table, this table. Now, let's maybe output that. You can do that also if you had a group code. You just don't calculate this new syndrome matrix or call it somehow differently so that you don't lose your original one. And let's maybe display this table. I do have some cheat sheet here to actually make this smooth. Make smooth output of error vectors table and syndromes. So we are going to go through the for loop, but before that we actually need to construct this matrix of error vectors, which is identity, well, flipped identity matrix actually, yes, 7 by 7, so of size m. So that would be r vec I 7, well, flip left right. Yes, so let's check if it's that one. And what I want to do now is to have a line here and list all the syndromes like that. Now, if you have, okay, let's add some comment here. So if group code don't flip, if cyclic code do flip left right. Yes, so now I do display cyclic code. So I do this flipping, and now I'm going to print that. Well, for that I need to prepare a format of matrix A, which is going to be replicated matrix of having this %2d, which is an integer number with two positions. Let's have fprintf format. And I want to have one row of the length of, well, in my particular case, that would be m. Format b, that's the error vector format, which is length m. Format b, that would be same format, except that the length now is going to be r. That's the syndrome format. Then I make a for loop from 1 to m, j equal to, wait, I have insert, j equal 1 to m, fprintf, I actually going to say it like that, format a, then vertical line, format b. So first error vector, vertical line, syndrome. Yes. Then new line. That is the format of the string what we wanted to output. And the output itself, that's going to be placed instead of these 2D, and instead of this 2D is accordingly going to be for the error vector rvec, and for the syndrome matrix like that. And so this is a little bit tricky part related to formatting, but it's wait, why I have 7 here? I need to actually have m first of all, and I do need bracket here. Yes. I think I would want to have extra space here just to make it smoother. Not sure if it works. Yes, it works. So now you see, yes, the error vector and its corresponding syndrome, just like that. And what I was speaking about in the lecture all along was that you have enough of unique syndromes here. See, they are non-repeating syndromes. Now let me just get some higher higher power generator polynomial. So let's go here and say, okay, now I'm going to use m equal to 31, k is going to be 25, r is going to be 5, and gen pol is going to be, I don't know, let's just pick one of these. So let's say, for example, this z5, z2 plus 1. Yes. So that's going to be power of 5 is 1, power of 4 is missing. Yes. Power of 3 also missing. Power of 2 present. Power of 1 missing. Power of 0 present. So this is generator polynomial of length 5, fifth degree, which is going to produce 31 different unique reminders. So let's see if it's actually so. And now I have something not working at the line 50. That's because I need to have this one after I have specified r. That was created for r equal 3. Now r is 5. So this produced the first one properly. And then at line 48, And I also need to set this to zeros. Okay, so syndrome matrix is zeros m by r. So now you have this table. Imagine having to calculate that one by one by running this division like here, 31 times. That would be obviously too big work. Luckily, you don't have to. As you can see, we can write a program. And again, all of these reminders are non-repeating, unique, meaning that every possible error that can happen in 31 symbols is going to have its own unrepeatable, unique identifier as this syndrome. That is only happening thanks to the fact that the generator polynomial has been properly selected. Now let me change it. Let's say I add 1 here. And see what happens if I use some other generator polynomial. Now we can see we start repeating. And here, and here. See, they are no longer unique. So if you get a reminder 0, 0, 0, 0, 1, it can be error in the symbol number 31. It can be error in the symbol, well, whatever that is, or it can be error in the symbol number 3. All of them have the same syndrome. That's not working because this polynomial doesn't meet criteria. It probably can be reduced by factorizing it in factors, yes, or it doesn't divide properly those binomials, yes. So my first recommendation would be to, if you have cyclic code, to actually check this one, if they start repeating or not. And if you don't have an error and see they do repeat, that means I have specified not proper generator polynomial for you, so you should contact me then. Yes. Okay, with that in mind, now we have our syndrome vector table. Let's maybe switch it to smaller scale, yes, like this back. And now I want to have encoding matrix for cyclic code and decoding matrix for cyclic code. Well, regarding decoding matrix, I believe we are all set. Almost, yes. Though we need to flip it vertically, and that's it. Yes, only vertically, or horizontally also. No, only vertically. So let's maybe start with that, because it's faster and easier, and we are going to need that. So that would be the cyclic code matrices. We'll start with decoding matrix, which is a syndrome matrix flipped vertically, upside down, UD. So if you flip horizontally, that's left to right. If you flip vertically, that's up to down. Yes? That's it. That's a decoding matrix. As for encoding matrix, sorry, we need to have the same thing. Yes, we still need to flip it. So we kind of create an encoding matrix from decoding matrix by removing the last R positions. So we say that this is from 1 to K rows that we keep, and all the others we remove. So that would be encoding matrix, which is decoding matrix from 1 to K, which is not complete yet. It's still only the, how we could put, equations part. Yes, we also need to have identity matrix here added. Yes, which is not so difficult. We already even have that I matrix. So I'm going to, so that's going to be extract equations, and then encoding matrix is going to be concatenated with I matrix and itself. Add in front I matrix. Now we have both of them. We have encoding and decoding matrices. Here is for cyclic code. Here it was somewhere for group code. Well, it's not printed anymore because I probably commented it. Yes, yes. But anyway, regardless of whichever matrices you have at this point, again, you can, and it's completely commendable if you want to, just write them down manually like so, and then specify them directly like this. Why not? It's also going to work. I just wanted to make sure you know how you can code this to check if you have created your matrix properly or not. Yes, and this one should be correct. Now, anyway, after you have these matrices now, so let's maybe separate this somewhat like more visibly. We are going to do 3 points. Point A, encode the message. So we need some data, which in my case 1010. Yes. Let's double check it. So I'm going to use cyclic one, but at this point it doesn't matter if you have group or cyclic or whatever else. Yes, the procedure of matrix encoding is the same for all of them. So yes, here it's 1010. It's just the matrix itself that's going to be different. Now we are going to make a code word by making a product of encoded matrix, which is, no, wait, data. So we need to have this for, so that is our encoding matrix, and that is our data, 0, so 1, 0, 1, 0, which we multiply matrix-wise. So you take this row, this column, add them together, get one symbol. Row, column, add them together, get one symbol. And specifically for the first ones, as you can see, they do not change the symbol itself. Yes, so here the first ones means that you are going to have 1, 0, 1, 0 as it is, and only then it's going to start adding something. Yes, so then it's going to create your control symbols like that. So let's see if it's so or not. So data multiplied by encoding matrix. Well, almost. Almost, except that regular matrix product actually does normal adding, regular adding, not XOR adding. So we have 1 plus 1 equal to 2, not 0. Yes, which is possible to be solved if you say, I want to calculate the remainder of all that stuff by dividing by 2. Now it's going to add and then calculate remainder, which is now producing the proper code word. Now that is our code word. Now I am going to do part B, say encode the code word without errors. And I'm going to create a new array consisting of message and say the message is the same as code word. Then I'm going to say C, and I will skip decoding for the last. As I said, I'm going to decode B, C, and D with just one command, as easy as that. So decode code word with one error. So now I'm going to say that message is my existing message, and as a new role, I'm going to add a code word and I'm going to corrupt message second row. Let's say, I don't know, let's be actually the same way as it was here. So we are going to corrupt this second symbol in the second code word. Yes. Now the decode code word with two errors. Message is going to be further appended by code word, and I'm going to corrupt that. Sorry, message 22. I didn't actually say what it is. It's actually whatever was there uh, plus 1 divided by 2. Well, I could have tried to invert it. Probably it would work, but I just want to be sure that I do XOR with plus 1 here. So now I'm going to copy this line. Message 3, third code word, is going to have error in the second position and also in the fifth position. So I'm going to copy this one again. So that adds error in position 2. That adds error in position 5. Now let's check what we have inside of our message and how we are going to decode it. So now our message consists of three code words. The first code word has no errors. Yes, so it's original code word. The second code word has error in the position number 2. The third code word has error here and also error here. Two errors, yes? One error and two errors. And what I say now is that using the decoding matrix, I am going to calculate all three syndromes with one hit. And actually you can calculate millions of them with one hit. It's only going to be restricted by the memory of your computer, the architecture, and all that stuff. And the size of the matrix, of course, also. Because, well, I have code word like 7, but you may have code word length, let's say 1023, or even longer than that. That's obviously is going to require more resources. So decode all three code words with one command. And that is going to be syndrome equal to, again, remainder by 2 of a message multiplied by the syndrome matrix, decoding matrix, dec matrix, yes? So if we run it, we are going to get three syndromes. One is saying that there is no error whatsoever. This says that the error, according to the table of error vectors, is in position number 2, which is correct. And this says that the error is in the position number 4, which is wrong. But we know how we can verify that we did properly is that we actually created errors in the position number 2 and position number 5. So that is 100 plus 111, and that produces the expected syndrome here. Yes? So you can verify that also because it adds syndromes together as well if you have multiple errors, just like it adds error vectors. And that's what you are going to get. It's not difficult to predict that if you were to introduce errors in the position 2 in the position 4 and in the position 5, then the syndrome would be 0, 0, 0. Although you have 3 errors, it says everything is fine. Yes, it's specific combination of errors. For other combinations of errors, it still might show some syndrome, one of the 7, nothing new here, which is pointing to the 1 position, which is not going to be real anyway. Okay, so that concludes the demonstration how you can use MATLAB to actually generate these matrices and then check yourself if you have correctly calculated these tasks. Yes, so basically that's whether you correctly obtain these syndromes or not, and whether you correctly or not have created the table of error vectors and syndromes specifically for cyclic code. Because for group code, it's straightforward and easy. Are there any questions? So if you will have questions, if something will be not clear, we'll still have more exercises in class. You still can email me. So be in touch. Yes, thank you for attention.